All right, welcome to the lesson. Okay, I'm going to continue on another of the group studies. So far, we have learned about the periodic table of how there are various trends, as well as the properties of the elements in the groups, as well as understanding how the periodic table is arranged, where all the elements, they have their own individual atomic number. Uh, However, the position is really based on the number of protons that they have. They are also arranged, or rather, they are assigned in groups as well as periods. So the groups and periods really depend on two things. The first one is the number of valence electrons, and the second thing is the number of filled electron shells. Previously, we have also looked at group 1 elements, which are known as the alkali metals. Today, we are going to be looking at another group of elements called the halogens. Now, the halogens all belong to group 17. And being in group 17 means that they all have a certain number of valence electrons. I hope that you're able to tell me that for these elements here in group 17, they all have 7 valence electrons. Now, what is special about the halogens is that they are, apart from them being all non-metals, they are also colored. So we have many non-metals around us, such as our oxygen, nitrogen, hydrogen, but these elements here, the halogens, they do have color, unlike the other gases that I've just mentioned. They are all colorless. They also exist like O2, H2, as well as N2. They exist as diatomic molecules. And I'm going to now talk a little bit about this term diatomic. Now, this term diatomic really means that the two atoms are covalently bonded to each other. All right, and you may write this down on your textbook as well. This is a very important definition to help you to understand what the term diatomic means. So diatomic means two atoms, di being the prefix for two, okay, and this kind of a molecule are always covalent molecules. And I've also written down on the right side where, I've written down the names of the various halogens. So altogether, there are 6 halogens that are in the periodic table. And all these halogens, they have a certain set of properties. So two main physical properties that all halogens have is that number one, okay, they have low melting points as well as boiling points. And number two, they are all colored. And these two properties, they eventually give rise to a series of trends. Okay, and I'm going to show you these two trends. Is that the first trend is that for all our halogens, the melting points and the boiling points increase down the group. And secondly, the colors also become darker. That means the colors, the intensities of these colors intensify and increase. So what I mean by the colors become darker is this, all right? Chlorine, which is the second halogen, is a yellow-colored, yellow-green gas at room temperature and pressure. But the next halogen, bromine, is now a red-brown liquid. And again, the next halogen, iodine, has become a purple-black solid. So you can see two things. Number one, you can see that the appearance in terms of color has become darker. So from yellow-green to red-brown to purple-black. And at the same time, you can also see that the physical state has changed. So from chlorine, which is a gas, to bromine, which is a liquid, and iodine, which is a solid. And the melting point and boiling point, you can also see that they are low because they are in the either minus 101, which is low, or just 114 for our iodine. And compared to metals, which can have melting points of 1,000 plus or 2,000 plus, okay, this is really considered low. Now, in your textbook, you have the diagram that shows you the colors of chlorine, bromine, as well as iodine. And in our syllabus, we'll be focusing on these three halogens. So do be familiar with their colors. Now, So number one, okay, I think the most important trend is in terms of the colors. So the colors will become darker down the group. Okay, and usually what happens is we can use this particular trend to deduce, okay, the color of our next few halogens. So in this case, since astatine is below iodine, okay, in group 17, therefore we can say that, quite safely, that astatine will have a black color. And also in terms of its physical state at room temperature and pressure, since iodine is already a solid, therefore astatine will also be a solid. So I'm going to type this down. So since iodine is a solid at room temperature and pressure, therefore astatine, which is the element, it will also be a solid. Okay, feel free to pause the lesson if you need some more time to write down all this information. Okay, I'm going to move on to the next bit on page 251. And now we're going to look at our chemical properties of halogens. Just like how our Group 1 alkali metals, in terms of the chemical properties, is really about the chemical reactions that they undergo. So for group 17 elements, it is also about the chemical properties is also about the kinds of chemical reactions that they undergo. Now, in this case, we will focus on not the things that they react with, but in how they react. So over here, we are going to be a little bit more concerned with how they are reacting. And in group 17 halogens, they all have 7 valence electrons. Okay, therefore, what they need to have is just one more electron in order to have that electronic configuration of a noble gas. And because they have the ability to attract that one electron, therefore the charge of the halides, which is the anions, the name that we give the anions, okay, the charge of all these halides will always be -1. All right. And having said that, okay, therefore our astatite ion will have a charge of -1 as well. And for astatite, it will be At with a minus at the top, right? This is how we will signify, or rather how we will represent the formula of the astatite ion. Now, the trend, okay, is again another important thing. Remember, in periodic table, we are always looking at trends of our elements. So in terms of the group 17 elements, okay, the trend in terms of the reactivity will be that the reactivity decreases down the group. So what this means is that our halogens become less reactive. So our first halogen, fluorine, okay, followed by chlorine, bromine, iodine, astatine as our usual common, more common halogens. So which is fluorine. And as you go down this group, you will expect the last few halogens to be very unreactive. So in this case, astatine as well as tennessine will be the two most unreactive halogens. Now, because of this, or rather, why is it that the reactivity decreases down the group? Now, this is, I hope that you have also noticed that this is opposite to the alkali metals, because in alkali metals, the alkali metals actually become more reactive down the group. Okay, for example, lithium is the least reactive of group 1 elements, but our francium, cesium, they are even more reactive than the previous few alkali metals. So this is really the opposite. For halogens, is really the opposite of the alkali metals. And why is that so? Okay, the reason lies in the size of the atom. Okay, the atomic size of our halogens increase down the group because there are more and more filled electron shells. Now, this makes it very difficult for the nucleus to attract that one more electron. All right, so because it is harder to attract that one electron, therefore reactivity decreases. Now, because of this difference in reactivity, now halogens, they undergo a very special reaction called a displacement reaction. Now, this displacement reaction is a reaction whereby one element takes over the place of another element in the compound. So the analogy that I have is this, right? Imagine that there is a powerful king in a kingdom, and there is another less powerful king in another kingdom. So what happens is that displacement reaction is where the more powerful king will take over the kingdom of the less powerful king. It will displace the less powerful king. So in our example for halogens is that, a halogen that is more reactive will be able to displace or take over the less reactive halogen's place. All right. So this is one example over here. You can look at this equation that is found in your textbook, page 251. And in this case, I'm going to highlight the two halogens that are featured. The first one, of course, is chlorine, which is in the elemental state. The second one is the bromide, which comes from bromine. Okay, and what happens is that because chlorine is above bromine in the periodic table in group 7, therefore it is more reactive and it can displace the bromide ions, and in turn, okay, it will become sodium chloride and it will displace the bromide ions to form bromine. Right? So this is what a displacement reaction looks like. Your more reactive halogen, in this case chlorine, will displace the less reactive bromide ions to form sodium chloride and bromine. So the bromine will be the element, and your chlorine will become ions in the chloride solution. Okay, let me just reiterate here. So you can write the words, the chlorine, okay, is originally in the element form, and after that it reacts with the bromide in the compound, and the chloride becomes part of a compound, and the bromine is displaced as an element. So this is what happens in a displacement reaction, whereby a more reactive halogen can displace a less reactive halogen in a compound. Now, if I do it the other way, all right, that means if I react bromine with sodium chloride, for example, then because bromine is less reactive, therefore it cannot displace chloride from sodium chloride. Right? So this is, okay, I'm going to give you one example at the bottom of this page. You can also write this down in your textbook. So let's say if I have fluorine, okay, reacting with sodium iodide. Now, because our fluorine is more reactive than sodium than iodide ions, therefore the fluorine will become iodine, because fluorine is more reactive than iodine. Now, if I have another case, another scenario, let's say I add bromine, okay, to sodium fluoride. Now, in this combination, because bromine is less reactive than fluorine, therefore there will be no reaction here. Okay, so no reaction, or rather no visible reaction, because bromine is less reactive than fluorine. All right. So this is the idea, the concept behind our displacement reactions, in which the more reactive halogen displaces the less reactive halogen. All right, so this is a rather short lesson on group 17 halogens, and I hope that you will be able to know the differences in terms of the trends, as well as the kinds of reactions and how the halogens actually react with each other.